Okay, so last time we talked about the long run of polynomials. Remember, basically the long run, like you guys saw in your warm-up again, the long run of a polynomial is determined by what? The leading term, right? Okay, the long run behavior is determined by its leading term. So what we were doing last time was looking at the polynomials kind of on a big scale. What we're doing today is focusing in on what we call the short run, looking at the specific things that are happening in these different functions. So I asked you guys to put those 3 functions on your calculator. And if you're just on your standard viewing window, you get just nonsense. Like, you can't even tell what function's what. Here's what I'd like you to do. We are first going to look at these on the long run, on a big scale. Go to your window. The only thing I need you to change is the y maximum value, and I want you to change that to 1,000. Okay? And then I want you to graph them. So there's the first one. There's the second. And there's the third. So on the long run, what do you see? Yeah, basically on the long run, you see a parabola. Those 3 graphs, those 3 functions have graphs that look very much alike, right? Okay. So this doesn't have to be super accurate, but ooh, that was bad. But just kind of sketching. Basically on the long run, we have 3 parabolas, which makes sense because what's the leading term of all 3 of those functions? X to the 4th, and the graph of y equals x to the 4th is a parabola. Makes sense. They all have the same leading term. They're all going to have the same long run behavior. All right. So now what we want to look at is each one of these functions on the short run. Basically, what's happening like kind of in the middle of the 2 big arms, like what's the specific stuff that's happening? So here's what I want you to do. Back on your calculator. Go to back to Zoom 6, your standard viewing window. And you'll get all 3 of those functions again, and it's going to look like trash for a minute. But we're going to then look at each one of these by themselves. So this might be a new calculator trick for you. Go to y equals. Do you see how all 3 of those equal signs are highlighted? So what I want to do is I want to graph just the first one. So I'm going to go down to the equal sign for y2, and I'm going to hit enter. And basically it's telling my calculator I want that function in there, but I don't want to graph it right now. So take off or deselect y2 and y3, then go back to your graph and it will graph just that first one that you have selected, okay? Now, we do want to change our window just a little bit because right now we're still not seeing the very bottom of that. We're not going to have to change it a whole lot, but go to your window. We need to increase the y minimum just a little bit. We can try, I guess, negative, I don't know, 15. That might work. If not, we can always adjust it. Oh, that's still not enough. So let's try, I should have written down what I needed, but I didn't. Let's try negative 20 for our y minimum. Still not enough, but yeah, that's close enough. We're getting a pretty good idea.
So what was it? Y
Negative 25. I should write that down.
Negative 30.
Negative 30 words.
Negative 30. Okay. So just kind of sketch that. And you don't have to be like super specific, but you can see kind of the values that your graph is going through on the x and, oh, that was bad, x and y axis. Just kind of get like a general sketch, and that was pretty terrible, but. All right, so then what I want you to do is go back to your y equals. I want you to turn y1 off, and I want you to turn y2 on. Again, to do that, select or deselect the equal sign, and then hit graph. The window that we have already works nicely for this, so we have kind of a W-shaped graph in the middle. Again, just a quick sketch will suffice for what we're looking for. And then finally go back to your y equals, turn off number 2 and turn on number 3, and graph that guy. And then a quick sketch of what that looks like, okay? Definitely not like super accurate, but that's okay. We'll get to be accurate here in just a minute. All right, so what do we notice? We kind of already discussed on the large scale or on the long run. We talked about that all 3 graphs resemble y equals x to the 4th, which again makes sense because they have the same leading term. But once we look at each one on the smaller scale, those 3 functions are definitely not graphing the same way, right? We have different places where they're crossing the x-axis, okay? So their zeros are all different. We have different number of bumps. So I really want you guys to understand what it means when we talk about the long run and the short run. Okay? Long run is on the big scale, like way zoomed out, just very, very general. That's your leading term. On the short scale, or the short run, that's your smaller scale. That's like the specific number of zeros and bumps that are happening in that function. Okay? All right. So what we're going to focus on today is the short run and actually finding those zeros and finding the number of bumps that a polynomial might have, okay? All right. Since the long run behavior is determined by the leading term, we always have looked at that in standard form, okay? To determine zeros and the short run behavior, we need to look at our polynomial in factored form. So when we go to this first example, it says to investigate the short run behavior of that function, we're eventually going to, and it kind of walks us through the steps on this first one, it's going to have us factor that polynomial, okay? Long run in standard form, short run, we want to look at it factored. So part A says to rewrite f of x as a product of linear factors. All that means is factor this out, all right? So what's the first thing that you guys see that we can do to factor that? Yeah, take out a GCF of x, so that leaves me with x squared minus x minus 6. And then how can we then factor that trinomial? Haley? Yeah, so there's a reason why I had you guys do that factoring review last time. It's because I should be able to just ask you real quick and you should know how that factors. Yeah? All right, so part A is writing it in factored form. We have that complete. Part 2 is to find the zeros of f of x. This is just like finding the zeros for quadratics, which is a type of polynomial. We set each factor equal to 0 and solve if need be. So right away we get 1, 0 of 0. The second factor gives us a 0 of 3, and the third factor gives us a 0 of -2. Nothing new, right? All right, and then the third part is asking us to graph and then to describe the graph. It will also ask us where it crosses the x and y axis. So to graph a polynomial, we're not going to be like, again, super accurate, but we are going to be accurate in where we plot those zeros. So along the x-axis, I know I have a 0 at 0, and then at 3, and then at -2. You can then go ahead and put this function in your calculator. If you want to go back to the standard form of it to enter it, that's fine. You can also enter the factored form. It really makes no difference. I think it's a little bit quicker to do the standard form, but. So then once you graph that, again, you can see that this is crossing at the zeros that we found at -2, 0, and 3. What we're looking for on the graph is just the direction of the arms. Okay, so it's starting down here, coming up, going through that 0. Just getting an idea of how to sketch that. Okay. All right, so now let's answer these two questions. We really already know the answer to the first. The graph crosses the x-axis at -2, 0, and 3. Those were our zeros. To find the y-intercept, or where it crosses the y-axis, here is what we are going to do. It's pretty clear where it is on this function, but for future reference, to find the y-intercept, you are going to substitute 0 in for all of your x's in the function. So y equals 0 times 0 minus 3 times 0 plus 2. Okay, I'm just substituting 0 in for the x. Well, 0 times anything is going to make that whole quantity 0. But again, just for future reference, when it's not super clear, you can plug in 0 for x to find the y-intercept. And then finally, the function resembles what on the long run? Yeah, y equals x cubed. So on the long run, it resembles y equals x cubed. Again, that's from the leading term. What questions can I answer? All right, so kind of summing up some of the things that we did in that example. We have polynomial p. If the formula for function p has a linear factor, that is a factor in the form x minus k, then p has a 0 at x equals k. and vice versa. If P has a 0 at x equals k, then it must have a factor of x minus k. That's something that you should have hit pretty hard in Algebra 2. I know I like drill my Algebra 2 classes on going from zeros to factors and vice versa. All right, let's talk about those bumps and number of zeros from those functions that you saw at the beginning, just in general. The number of zeros that you will have, this is for an nth degree polynomial. So you can apply kind of these general rules for whatever degree your polynomial is, but in general, if you have an nth degree polynomial, you can have at most n zeros. So for example, a quadratic, that's a degree 2, right? How many zeros do you typically have with a quadratic? 2, okay? That's all that means. You can have at most n zeros for an nth degree. The number of bumps that you will have in a polynomial will be one less, for the most part, one less than the degree. Okay? All right. Now, there is the situation where you could have a multiple zero. It could be a double zero. It could be a triple zero. It could be anything. So this will happen if you have a repeated factor. So I give you kind of the two general situations that you might have. If you look at this first function, s of x, think about expanding that out. We could rewrite that as x minus 4 times x minus 4, right? If I asked you to find the zeros, what would it be? 4, but you have that double zero, okay? Okay, so in general, if you have an even number of repeats, meaning that exponent is an even number, here's what will happen in the graph. For an even number of repeats, the graph will not cross the x-axis. It will kind of bounce off the x-axis at that zero. So if you have a zero where the graph does not go through it, you're going to have a multiple zero. If it is even, then it kind of bounces right off of where that zero is. For an odd number of repeats, so you can look at this example, the quantity x plus 1 cubed, that would be an odd number of repeats because we have an odd exponent. What happens here is your graph will cross the x-axis at that zero, but it will look flattened there. So you can kind of see at this example at that -1, this would be like a triple zero. It is crossing that zero, but you kind of see how it's flattened out right there around the zero, okay? We're going to do a little bit of practice here identifying when we'll have a multiple zero because they're really easy to forget about. All right, the very last thing that we are going to do is write a formula for a polynomial given its graph. Do you have any questions that I can answer so far before we finish this up? Okay, so let's look at the first one. The directions are to find a possible formula for that polynomial. Here is kind of the thought process that I go through. The very first thing that I do is list out my zeros. And that's just a matter of looking at where your graph is crossing the x-axis. So ladies and gentlemen, tell me where my zeros are. -1 and where? 3. But look at what is happening at 3. Your graph is not crossing at that 0. So what must be happening there? It's going to be a double, okay? Because it is bouncing off at 3, that is a double zero, and so I'm going to list 3 twice. Now that I have the zeros listed out, from there, I'm going to list out the factors that must be in that polynomial based on the factors. So if -1 is a 0, what must be a factor? A factor. X plus 1. If 3 is a 0, what must be a factor? X minus 3. And then again, we have, because it's a double zero, we're going to have 2 of the same factors for that. The next thing that I am going to list that I'm going to use here in just a minute is just another point on that graph. Another point that's not a 0 point. So in this case, the other point that I am given that's on that graph is 0, -3. I'm listing that out right now. I'm going to use it here in just a second, just a smidge. Okay. So y equals, starting to actually get to my function now. I know that my function has those factors, x plus 1, x minus 3, x minus 3, but it may also have some coefficient. Remember that coefficients do not factor into finding zeros. So when we're working backwards, we have to think about that there might be some constant in that original function. That's where this other point comes into play. So what we're going to do is use that other point as values of x and y to find that coefficient or that constant. So what I'm going to do is I'm going to go through, I'm going to plug in -3 for y from that other point. I'm solving for k, so that's staying there. And then I'm substituting 0 in for all of my x's. And then it's just a little bit of algebra, just solving for k. I will go ahead and go through and say, well, 0 plus 1 is 1. Then -3 and -3. I'll simplify that right side up a little bit. So 1 times -3 times -3 is what, +9? So k is -1/3. Once I know that value, then all I need to do is substitute that back into the function that I had started, and I did go ahead and write that x minus 3 as a quantity squared.